No power plants, no tangled wires, just pure, clean energy drawn right from the Earth itself. It sounds amazing, almost like science fiction, doesn't it?
Yeah.
This whole idea of harnessing our planet's power, specifically its magnetic field, for electricity. And today, you and I are taking a really deep dive into one specific proposal. The idea that maybe we could amplify the Earth's naturally weak electromagnetic field, maybe using something like a Tesla coil, to actually generate usable power.
Right. And our goal here for this deep dive is to really take that idea apart piece by piece using science. We need to look at the three core components. First, what is the Earth's geomagnetic field, really? Second, how does a Tesla coil actually work? What does it do? And third, we have to bring in the fundamental laws of physics, thermodynamics, electromagnetism, the rules that govern everything. They tell us what's possible and what's just not. So our mission is to give you a clear, evidence-backed verdict. Is this scientifically feasible or not?
Okay, let's unpack this then. Before we even get to pulling energy from it, we need a solid grip on what the Earth's magnetic field is. I think a lot of us probably picture, a giant bar magnet buried deep inside the planet just sitting there. Is that anywhere close?
That's a really common picture, but no, it's actually not accurate at all. The main reason is temperature. The Earth's core is incredibly hot. We're talking thousands of degrees Celsius. And that temperature is way, way above something called the Curie point for iron. That's the temperature where iron or any ferromagnetic material loses its permanent magnetic properties completely.
Ah, okay, so it's too hot down there to be like a permanent fridge magnet.
Exactly. So it can't be a static, permanent magnet that's just been there forever. Instead, what we understand now is that it's a dynamic field. It's continuously generated. The leading theory is called the Geodynamo theory. It describes this kind of self-exciting dynamo process happening way down in the Earth's fluid outer core. That's a thick layer, about 2,300 kilometers thick, made of molten iron and nickel that's constantly churning. And crucially, these metals are excellent electrical conductors.
Fluid outer core. So liquid metal.
Liquid metal, yeah. And it's convecting, moving around because of heat.
So it's this incredibly dynamic, self-powering engine deep inside the planet. What actually makes it work? What are the key ingredients?
Well, you need three essential conditions, and Earth's core meets them all. First, as we said, you need that electrically conducting fluid, the molten iron and nickel. Second, you need a continuous energy supply to keep it churning. This energy comes from a few places. Leftover heat from when the Earth formed, heat released as the inner core slowly cools and solidifies, and also radioactive decay of certain elements down there, like potassium-40 and uranium. All this heat drives convection, like water boiling in a pot, but on a planetary scale. And the third crucial ingredient is the Earth's rotation. This rotation introduces the Coriolis effect, which you might know from weather patterns. Down in the core, it organizes that chaotic churning fluid into these large-scale, helical, sort of spiraling columns.
Okay, so spinning, conducting fluid, and heat. How does that make a magnetic field?
Right, so these organized spinning columns of molten metal act like electrical wires. Their motion generates electrical currents. And then Ampere's law, a fundamental principle of electromagnetism, tells us that electric currents create magnetic fields. The clever part of the geodynamo is that these generated currents are oriented in such a way that the magnetic field they create actually reinforces the original field. It's a self-sustaining loop. This continuous regeneration is absolutely vital. Without it, the Earth's magnetic field would naturally decay and disappear in maybe 20,000 years or so, just due to electrical resistance, what we call ohmic decay.
Wow, okay, so it's constantly rebuilding itself. Now, here's where it gets really interesting for the proposal we're looking at. Even with this massive planetary engine running, just how strong is this magnetic field when it reaches us up here on the surface? And crucially, what's its energy density? Does it pack enough punch to be tapped?
That's the key question for energy harvesting. And the answer is, it's incredibly weak at the surface. We measure it in units like nanotesla or Gauss. It varies a bit, maybe 22,000 nanotesla near the South Atlantic anomaly, up to around 67,000 near the magnetic poles. To put that in perspective, 0.22 to 0.67 Gauss, your average refrigerator magnet. That's typically several hundred times stronger.
Hundreds of times.
Yeah.
Really? Okay, so it's weak. What does that mean for the energy it contains?
It means the energy is extremely diffuse. The energy density, the amount of energy stored per unit volume is incredibly low. The calculation gives us a value around 0.001 joules per cubic meter.
0.001 joules in a whole cubic meter.
Exactly. It's minuscule. Think about trying to power anything substantial with that. You'd need to process an immense volume of space just to get a tiny amount of energy. This incredibly low energy density is, frankly, a fundamental show-stopping obstacle for any idea of large-scale power generation directly from the field's energy.
Okay, weak field, very diffuse energy. So what does this mean for actually generating electricity? We often hear you need a changing magnetic field. How does that fit in? If the field is constantly being generated by the geodynamo, isn't that a change?
That's a really sharp question, and it gets right to the core of electromagnetic induction. Faraday's law of induction, which is the basis for almost all electric generators, states that you only induce a voltage, an EMF, when the magnetic flux through a circuit is changing over time. It's all about the rate of change, the dBd part of the equation. The main field, generated by the geodynamo, while dynamic over geological time, is effectively static or quasi-static on human timescales.
Quasi-static, meaning?
Meaning it changes incredibly slowly. We call it secular variation. For example, the overall strength, the dipole moment, is decreasing, but only by about 6% per century. For any device you or I could build, operating over seconds, minutes, hours, the main field looks like a steady, unchanging DC field, 0 Hertz frequency.
So no change, no induction.
Precisely. A constant magnetic field passing through a stationary coil induces 0 voltage. End of story for that scenario. Now, you're right to ask about changes. The Earth's magnetic field does experience rapid fluctuations on timescales of seconds to hours. We see these during geomagnetic storms. But, and this is crucial, these rapid changes are almost entirely external in origin. They're caused by the solar wind, the stream of particles from the sun, interacting violently with our magnetosphere.
So solar flares, CMEs, that kind of thing.
Exactly. Coronal mass ejections, solar flares, they buffet the magnetosphere, causing rapid changes in the magnetic field observed at the ground. And these rapid changes can induce currents. They cause what we call geomagnetically induced currents, or GICs, in long conductors like power lines.
Okay, so there are changing components.
Yes, but they're driven by the sun. The energy isn't coming from the Earth's internal dynamo. It's coming from the kinetic energy of the solar wind, transferred via the magnetic field. So this distinction is paramount. If you want to harness energy via induction related to Earth's field, you must target a changing component. The only components changing fast enough are solar-driven. The challenge for the proposal we started with isn't just amplifying a weak field, it's tried to extract energy from an essentially DC magnetic field using a device, the Tesla coil, which is designed for high-frequency AC. And physics says that just doesn't work.
Okay, that makes sense. Let's shift focus then to the device itself, the Tesla coil. For a lot of people, it conjures up images of, mad scientists, big sparks, maybe even those free energy ideas floating around online. But what is it, scientifically speaking?
Right, let's demystify it. The Tesla coil was invented by Nikola Tesla back in 1891. Fundamentally, it's an electrical resonant transformer circuit. Its specific purpose is to take an input electrical power and transform it into very high voltage, low current, high frequency alternating current AC electricity. And the first key point, it is absolutely not a passive device that somehow scoops up and amplifies ambient fields. It's an active circuit. It needs to be plugged in, powered up.
Active. Okay, so what are the main parts?
A typical spark gap Tesla coil, the classic design, has a few key bits. You start with a high voltage power supply, which takes mains voltage, say 120 or 240 volts, and steps it up to several thousand volts, maybe 5 to 30 kilovolts. Then you have a primary capacitor, which stores electrical energy from that supply. Next is a spark gap, basically 2 electrons with a gap between them. This acts as a very fast, high voltage switch. And finally, the heart of it, the resonant transformer. This consists of a primary coil, usually just a few turns of heavy wire, and a secondary coil with hundreds or even thousands of turns of finer wire, often round on a cylindrical form. You might also see a metal shape, like a sphere or torus on top. That's the top load, and it helps shape the electric field.
Got it. So it definitely needs power to even start. How does the amplification part work then? And what kind of output are we talking about, those big sparks?
Okay, let's walk through the cycle. The high voltage supply charges up the primary capacitor, like filling a bucket with charge. The voltage across the capacitor rises rapidly until it's high enough to break down the air in the spark gap, causing a spark to jump across. Zzz.
Okay, the spark jumps.
That spark effectively closes the primary circuit for a very brief moment. Now the capacitor rapidly discharges its stored energy into the primary coil. This combination of the capacitor C and the primary coil L forms an LC circuit. Energy sloshes back and forth between the capacitor's electric field and the coil's magnetic field extremely quickly, oscillating at a very high frequency. This rapid oscillation creates a powerful, rapidly changing magnetic field around the primary coil. This whole cycle shows it's an active process needing that initial power input. It's not passively collecting anything.
And the voltage step up. Where does that huge amplification come from?
That's where resonance comes in. The Tesla coil is designed as a double-tuned resonant transformer. This means both the primary circuit, L1 and C1, and the secondary circuit, L2 and its own capacitance, C2, including the top load, are carefully designed to resonate at the same very high frequency, usually somewhere between 50 kilohertz and 1 megahertz.
Like tuning two guitar strings to the same note.
Exactly like that. Or maybe a better analogy is pushing someone on a swing. If you push at just the right frequency, the resonant frequency, even small pushes, build up a huge amplitude, a really high swing. In the Tesla coil, the oscillating primary circuit gives precisely timed pushes of energy to the secondary circuit via the shared magnetic field. Because they're tuned to the same frequency, the energy transfer is incredibly efficient, and the voltage in the secondary coil builds up to enormous levels. This resonant gain achieves much higher voltages than you'd get from just the turns ratio of the coils alone. Like in a normal transformer, we're talking hundreds of thousands, even millions of volts.
Millions of volts. And the output is high-frequency AC.
Yes, very high voltage, but relatively low current, and crucially high-frequency AC. Typically in that 50 kilohertz to 1 megahertz range, and those spectacular arcs you see, they aren't really electricity in the sense of a wire carrying current. They are columns of air that have been ionized, turned into plasma by the incredibly intense, rapidly oscillating electric field around the secondary coil.
Okay, so the bottom line on the Tesla coil.
The bottom line is it's a power converter or transformer. It takes relatively low voltage, low frequency power from your wall, stepped up, and transforms it into extremely high voltage, high frequency power. It absolutely does not create energy, it just changes its form. And critically for our discussion, it's fundamentally an AC to AC converter designed for a specific narrow band of high frequencies. It cannot be driven by a DC source, like the Earth's essentially static magnetic field. A DC source can't make the capacitor charge and then rapidly oscillatorily discharge through the spark gap and primary coil. The whole operating principle relies on high-frequency AC input dynamics.
Right, this really brings us to the fundamental physics, doesn't it? Regardless of the specifics of the Earth's field or the Tesla coil, what do the basic laws of the universe say about this whole idea?
Exactly. Let's ground ourselves in the bedrock principles. First and foremost is Faraday's law of induction, which we touched on. Discovered by Michael Faraday way back in 1831, it's the foundation of pretty much all electrical generation. It states very clearly that the induced voltage, the electromotive force, or EMF, is directly proportional to the time rate of change of magnetic flux. That little DDT in the math is everything. It means voltage is generated only when the magnetic flux is changing.
And flux can change how? Moving the magnet, moving the coil.
Right. You can change the magnetic field strength, B itself. You can change the area A of the coil exposed to the field, or you can change the orientation, the angle between the coil and the field. But, and this is the crucial point, if you have a constant, unchanging magnetic field passing through a stationary, rigid coil, the rate of change is zero. TEP-DT is zero. Induced EMF is zero. As we've established for a stationary device on Earth, the main geomagnetic field is effectively constant DC. So Faraday's law immediately tells us this core idea of passively tapping the static field with a stationary device is a non-starter. It's the first major physical principle that invalidates the proposal.
Okay, so Faraday says no go without change. But what about the bigger picture? The sort of universal no free lunch rule, conservation of energy, how does that play in?
That's the next critical piece, and it's tied directly to Faraday's law through something called Lenz's law. Lenz's law is essentially the physical manifestation of the conservation of energy in electromagnetism. It's represented by that minus sign in Faraday's equation. It states that any induced current will flow in a direction that opposes the change in magnetic flux that produced it.
Opposes the change.
Oh.
What does that mean practically?
Think about a simple hand crank generator. You rotate a coil in a magnetic field. Faraday's law says this changing flux induces a current. Great, we get electricity. But Lenz's law says that induced current itself generates its own magnetic field. And that secondary magnetic field interacts with the original field in a way that creates a torque, a force, that resists your rotation. It pushes back against you.
Ah, so it gets harder to crank the generator when it's producing electricity.
Exactly. You have to continuously put in mechanical work. You have to expend energy turning that crank to overcome this magnetic braking effect and keep generating electricity. This clearly shows that the magnetic field isn't a source of energy to be consumed. It's a medium for energy conversion. It allows you to convert mechanical energy, cranking, into electrical energy.
Like a gear in a machine. It transmits force but doesn't create it.
That's an excellent analogy. The magnetic field is the gear. It facilitates the conversion, but the energy has to come from somewhere else, your muscles, a waterfall, burning fuel. So any claim to extract net energy from a magnetic field itself without putting in an equal or greater amount of energy in another form is essentially a claim for a perpetual motion machine. And the law of conservation of energy says those are absolutely impossible. No free lunch.
That's fascinating. So how does this connect to the energy that is actually stored in the magnetic field? You said it has energy density. Isn't that energy just sitting there waiting to be tapped, like a cosmic battery?
That's another subtle but important point. Yes, a static magnetic field does contain potential energy. We calculated its density. This energy represents the work that was done to establish the field in the first place. However, this stored energy is not freely available for extraction in the way you might tap a battery. To get energy out of the magnetic field, you have to change the field state, for instance, by causing it to collapse or by significantly altering its configuration. Think of the Earth's field. It's not a static reservoir like a full battery. It's in a state of dynamic equilibrium. The energy being put in by the Geodynamo process from heat and rotation is constantly balancing the energy being lost through Ohmic dissipation, resistance in the core.
So it's like a river, not a lake.
Yeah.
Energy flowing through, not stored up.
That's a pretty good way to think about it. It's an ongoing process. Attempting to just siphon energy out of this balanced system without providing an external input to drive a change would violate fundamental laws of thermodynamics. You can't just dip a bucket in and expect the river level to drop without consequence or affecting the flow. The field itself is the result of this continuous energy conversion deep within the Earth. It's not a primary fuel source just waiting there.
Okay, we've really dissected the Earth's field, the Tesla coil, and the fundamental laws. So let's bring it all together now. Why, specifically, when you combine these pieces, is this proposal to amplify the Earth's field with a Tesla coil just fundamentally impossible?
It boils down to a fundamental mismatch, a profound incompatibility. The core flaw is trying to link the quasi-static, essentially DC 0 Hertz nature of the Earth's main magnetic field with the operational requirements of a Tesla coil, which is an active, powered device designed exclusively for high-frequency AC. We're talking 50,000 to 1 million hertz.
So DC source, AC device. They just don't speak the same language.
Exactly. There is simply no known physical mechanism by which a static DC magnetic field can induce the necessary high-frequency oscillating current in the Tesla coil's primary circuit. It can't charge the capacitor in the right way. It can't trigger the spark gap repeatedly at high frequency. The physics just isn't there. And furthermore, even if you could somehow get it started, an operating Tesla coil generates its own powerful high-frequency magnetic field. This field would be orders upon orders of magnitude stronger than the feeble, static geomagnetic field in its immediate vicinity. The Tesla coil's field would completely swamp the Earth's field, making any purported interaction utterly negligible. They operate on completely different principles, different frequencies, different energy sources, and vastly different field strengths.
Wow.
It's like trying to drive a Formula One car with a bicycle pedal.
Right. What about other ways? Couldn't you say move the device rapidly through the field, or maybe find some way to modulate the Earth's field itself to create that needed change? We know moving a wire works, right?
Good question. Let's look at those. Scenario 1, moving the coil. Yes, absolutely. If you move a conductor, like a coil, through the Earth's magnetic field, you will generate electricity via Faraday's law. That's how a simple dynamo works. But remember, Lenz's law, the energy you get out comes directly from the mechanical work you put in to move that coil against the magnetic braking force. It's not free energy from the field. And because the Earth's field is so weak, the amount of power you could generate this way, even with a large, fast-moving device, would be incredibly tiny. Using a complex, high-voltage, high-frequency device like a Tesla coil for this simple, low-power DC generation task would be completely inappropriate and wildly inefficient. You'd use a simple dynamo circuit.
Okay, so moving it works, but it's not free and not suited for a Tesla coil. What about modulating the field, making it change?
Scenario 2, modulating the field. To do that significantly, you'd essentially need to create your own powerful fluctuating magnetic field using a large electromagnet right next to your device. This electromagnet would have to be strong enough to overpower and rhythmically distort the local geomagnetic field. But where does the power for that massive electromagnet come from? It has to come from an external power source. You'd be pouring huge amounts of energy into driving this electromagnet, and due to inevitable inefficiencies and thermodynamic losses, you could never hope to recover even a fraction of that energy through induction. It'd be a massive energy sink, not an energy source. You'd be consuming far more power than you could ever generate.
That makes sense. Now, you mentioned resonance earlier.
Yeah.
That word resonance seems to pop up a lot in these kinds of speculative energy ideas, almost like it's some kind of magic key. Can you clarify what resonance really means in physics and why it's being misused here?
Yes, that's a really important point. Resonance is a legitimate and powerful concept in physics, but it describes several different phenomena, and the term gets easily conflated or misused. Let's compare a few. First, there's the LC circuit resonance we talked about in the Tesla coil. That's about the rhythmic exchange of energy between an inductor's magnetic field and a capacitor's electric field within a closed electrical circuit. It happens at high frequencies, kilohertz to megahertz, and is always driven by an external power supply. It's used for tuning circuits, filters, and in the Tesla coil for voltage transformation.
Okay, that's the Tesla coil type. What else?
Then you have things like Schumann resonances. These are completely different. They are global, planet-scale, standing electromagnetic waves that exist in the cavity between the Earth's surface and the ionosphere. They're naturally excited by the electromagnetic energy released from global lightning discharges. Their frequencies are extremely low. The fundamental is around 7.83 hertz, with harmonics above that. They are fascinating for atmospheric science and monitoring global weather, but have nothing to do with Tesla coils or power generation.
Super low frequency, global scale. Got it. Any others?
Another important one is nuclear magnetic resonance, or NMR, which is the basis for MRI scans in hospitals. This involves atomic nuclei, which have a property called spin, precessing like tiny tops in a strong external magnetic field. When you hit them with radio waves at exactly their precession frequency, which depends on the magnetic field strength, typically megahertz to gigahertz range, they absorb that energy. It's a quantum mechanical resonance used for imaging and chemical analysis. Again, totally different physics requiring strong external fields and radio waves.
So completely different phenomena, all using the same word.
Exactly. The proposal we're examining seems to wrongly conflate these distinct concepts. There's no physical mechanism or theoretical basis for a high-frequency LC circuit like a Tesla coil to somehow resonate with or draw power from the Earth's static DC magnetic field, or even the ultra-low-frequency Schumann resonances. The physics just doesn't connect. And just to hammer home the infeasibility from an energy perspective, let's revisit that energy density, 0.0001 joules per cubic meter. Think about a single modest 100-watt light bulb. It consumes 100 joules of energy every second. To supply that power, even assuming you had a magical device with 100% conversion efficiency, you would need to capture and convert all the magnetic energy contained within a volume of 100,000 cubic meters of space every single second.
100,000 cubic meters, how big is that?
That's a cube of air measuring over 46 meters, about 152 feet on each side. Imagine trying to build a device that could somehow process that much volume every second perfectly. It just highlights how incredibly dilute the energy in the Earth's magnetic field is, making any large-scale harnessing utterly impractical, even if the fundamental physics allowed it, which it doesn't.
Right, the numbers themselves are just staggering in terms of impracticality. Okay, so if this specific idea, Tesla coil amplifying the Earth's field, is firmly in the realm of pseudoscience, what are the real-world scientifically valid ways our planet's magnetic environment actually interacts with energy? Or what legitimate frontier research is exploring related areas? What is possible?
Okay, let's talk about what's real. The most dramatic and powerful real-world example of large-scale electromagnetic induction involving the Earth's field is something we mentioned briefly. Geomagnetically induced currents, or GICs. These are real, measurable, sometimes very large currents induced in long man-made conductors like power grids, pipelines, even railway signaling systems. But again, crucially, they are not caused by the static geomagnetic field. They are caused by the rapid changes in the field that occur during geomagnetic storms, driven by intense solar activity like CMEs hitting Earth.
So it's the solar storm causing the change, which then induces the current.
Precisely. The storm rapidly changes the magnetic field at the surface. This induces a geoelectric field in the Earth's crust, and that electric field drives currents through any long conductors available. These currents can be huge, hundreds of amperes, but they are absolutely not a viable power source. They're uncontrolled, unpredictable, very low frequency, millihertz range, and primarily a hazard. They can overheat transformers, disrupt grid operations, and accelerate pipeline corrosion.
Like the Quebec blackout in '89, was that GICs?
Yes. The massive Hydro-Quebec blackout in March 1989 is the classic example. GICs tripped protective relays, plunging millions into darkness. So GICs are real, powerful induction, but the energy originates from the sun's kinetic energy, and it's a dangerous side effect of space weather, not a usable resource.
Okay, GICs are real but hazardous. What about truly cutting-edge research? Anything out there that might challenge our old assumptions, even if it's not practical power today?
Yes, there is some fascinating, legitimate frontier science. One example is the theoretical and experimental work done recently by Christopher Kiba, Jason Hand, and their colleagues. It's sometimes dubbed the Chiba-Hand loophole. For a long time, it was considered impossible to generate electricity from a conductor that's stationary relative to the Earth's surface, just sitting there. But they proposed, theoretically back in 2016, and then experimentally verified around 2025, a subtle way it could happen under very specific conditions.
The loophole, how does it work?
It involves a carefully constructed device, a hollow cylindrical shell made of a specific type of soft magnetic material called manganese zinc ferrite. And it has to be oriented very precisely, perpendicular to both the local Earth magnetic field vector and the Earth's rotational velocity vector at that location.
Okay, very specific setup. And what did they actually measure? Were they powering cities?
No, absolutely not. They measured a continuous, steady DC voltage of just a few microvolts, millionths of a volt, and a current of a few nanoamps, billionths of an amp. The power generated is utterly infinitesimal, a laboratory curiosity.
Microvolts and nanoamps. Tiny. But where does that energy come from, if not the static field?
This is the really clever part and why it's valid science. The power isn't free energy magically pulled from the static field. It's extracted directly from the Earth's immense reservoir of rotational kinetic energy. The device essentially creates an incredibly tiny magnetic braking effect on the Earth's spin. So the energy comes from slowing down the Earth's rotation by an immeasurable amount.
Wow. Okay, so it's tapping Earth's spin, using the magnetic field as the go-between.
Exactly. It's a beautiful, subtle demonstration of fundamental physics, a non-resonant DC phenomenon. It reinforces the principle that valid energy extraction methods need to tap into some existing energy flow or reservoir like solar wind kinetic energy for GICs or planetary rotational energy here using the magnetic field as a conversion medium. It's fascinating science, but light years away from being a practical power source.
That's really cool, actually. A genuine, subtle effect based on solid physics. Now, we can't really wrap this up without touching on Nikola Tesla himself again. He was clearly a brilliant inventor. What was his big dream with wireless power, and how does it hold up against modern physics?
Right, Tesla was undeniably a genius, especially with AC power systems. His contributions there literally power our world. We have to give him enormous credit for that. His later, grander vision, however, was the world wireless system. The idea of transmitting not just information, but significant amounts of electrical power globally, without wires, possibly using the Earth itself or its atmosphere as a conductor. He conducted famous experiments, particularly at Wardenclyffe Tower, exploring high-voltage, high-frequency resonance. He might have even detected things like the Schumann resonances without fully realizing what they were, but his theoretical framework for how large-scale wireless power transmission through the Earth would work, well, it just doesn't align with our modern, experimentally verified understanding of electromagnetism.
Why not? What's the problem?
Primarily, energy losses. Transmitting power electromagnetically over long distances without highly directional beams, like microwaves, which have their own issues, is incredibly inefficient. Energy spreads out, it gets absorbed and dissipated by the environment, the ground, the atmosphere. The losses would be colossal, making it completely impractical for bulk power transmission compared to wires. So while his vision was ambitious and demonstrated his incredible imagination, it remains just that, a dream, not a physically or economically viable blueprint for powering the globe wirelessly. So let's synthesize everything we've discussed into a final verdict on the original proposal. Generating electricity by amplifying the Earth's magnetic field with the Tesla coil. Based on our understanding of the geomagnetic field, the operation of a Tesla coil, and the fundamental laws of physics, Faraday's law, Lenz's law, conservation of energy, thermodynamics, the conclusion is unavoidable. This proposal is unequivocally unfeasible. It's crucial to understand this isn't just an engineering challenge waiting for a clever solution. It's a physical impossibility based on the established laws of nature. To recap the key reasons. The fundamental incompatibility between the Earth's quasi-static DC field and the high-frequency AC requirements of Tesla coil. The direct violation of Faraday's law requiring a changing magnetic flux. The violation of energy conservation, no free energy from a mediating field, the misapplication of the concept of resonance, and finally, the prohibitively low energy density of the geomagnetic field itself, making large-scale extraction impossible even if the physics somehow allowed it.
That's a very clear and definitive conclusion. So what's the takeaway for us, as curious people trying to understand the world? When we hear about these big, exciting, maybe slightly out there ideas, how do we navigate that information? How do we tell the difference between something like the Chiba hand experiment, which is real but tiny, and something like this Tesla coil idea, which just isn't possible?
That's perhaps the most valuable lesson from this kind of deep dive. It really highlights the critical distinction between legitimate frontier science and what we have to call pseudoscience. Pseudoscience often grabs onto real scientific terms like resonance, frequency, magnetic field, but uses them incorrectly out of context, or in ways that sound impressive but lack actual physical meaning in that application. It frequently proposes mechanisms that would flat out violate fundamental, well-established conservation laws, particularly the conservation of energy, often promising free or limitless energy. And crucially, pseudoscience lacks a foundation in rigorous, peer-reviewed, independently verifiable experimental evidence. Claims are often anecdotal, rely on misinterpreted observations, or simply cannot be replicated under controlled conditions.
And legitimate science.
Legitimate science, even the really cutting-edge frontier stuff like Chiba hand, always builds upon established laws. It might find unexpected consequences or subtle loopholes within those laws, but it doesn't claim to overthrow them casually. It makes specific, testable predictions. And most importantly, it undergoes a rigorous process of peer review, critical scrutiny, and attempts at independent replication by other scientists. That's how scientific knowledge progresses reliably. Learning to spot those differences, the misuse of terms, the violation of core principles, the lack of verifiable evidence is key to good scientific critical thinking.
That's incredibly helpful. So for those listening who are genuinely intrigued by the real amazing physics of our planet's electromagnetic environment, and clearly there's a lot of fascinating stuff there, where should they direct their curiosity next? What are the legitimate avenues to explore?
Oh, absolutely. If this discussion has piqued your interest in the real science, there are many fantastic areas to explore further. You could delve into magnetohydrodynamics, the physics of conducting fluids, like the Earth's core, and really dig into geodynamo theory. Understanding how our planet generates its own magnetic shield is just mind-blowing stuff. Another vital area is space weather and the study of geomagnetically induced currents, GICs. This connects solar physics to real-world engineering challenges right here on Earth. It's incredibly relevant. You could also investigate low-frequency electromagnetics, which includes phenomena like wave propagation in the Earth ionosphere cavity and those mysterious Schumann resonances. And finally, for those really keen on the cutting edge, keep an eye on the peer-reviewed scientific literature. Look for research on novel energy conversion mechanisms, maybe follow-ups by independent groups on things like the Chiba hand experiments. That's where you'll find the genuine progress, validated by the scientific community.
Fantastic. So by focusing on these legitimate established fields, you can really engage with the truly fascinating and complex physics of our planet and its space environment without getting sidetracked by ideas that, while maybe imaginative, are ultimately scientifically impossible. Thanks so much for joining us on this deep dive and for shedding light on such a complex topic.